So, how do you predict the unpredictable? In a cardiac intensive care unit, every single minute and every single bed is absolutely critical. But what if you could use math to kind of peek into the future of a patient's stay? Well, today we're going to dive into a really fascinating study that tried to do just that, using the power of mathematics to bring a little bit of clarity to the chaos of the ICU. All right, here's our game plan. First, we'll tackle the big problem hospitals are up against. Then, we'll open up the mathematical crystal ball they use to solve it. We're going to see how they actually scored patients, what the model spit out, how they put it to the test, and, of course, what this all means for the future of medicine. Okay, so put yourself in this situation. You're running a cardiac ICU. You've got a fixed number of beds, a limited number of staff, and only so many resources to go around. Planning is, well, it's everything. The problem is a patient's journey is just notoriously complex and uncertain. Trying to get a solid handle on how long someone might need that critical care, that is a massive, massive challenge. Which, brings us right to the core question here. How do you forecast something as complicated as a patient's length of stay in an ICU? An accurate prediction isn't just some interesting academic puzzle. It's absolutely crucial for managing patient care efficiently, for allocating those precious resources, and at the end of the day, for saving lives. So the researchers in this study, they didn't turn to a literal crystal ball. Nope, they turned to something way more powerful, a mathematical model called a Markov chain. So let's pull back the curtain and see how this brilliant tool actually works. So what on earth is a Markov chain? Well, at its heart, it's just a way to map out probabilities. You've got a system that can be in one of several states. The model then calculates the chance of moving from, say, state A to state B. But here's the key, the really crucial part. It has a memoryless property. What happens next only depends on where you are right now, not the long, winding road you took to get here. To make that a little more concrete, just think about a super simple weather forecast. A Markov model wouldn't care if it was snowing last week or hailing yesterday. It would just ask one simple question. Given that it's sunny today, what is the probability it will be rainy tomorrow? It's all about the odds of the very next step, based only on where you're standing right now. Okay, so that's great for weather, right? Sunny, rainy, cloudy, easy. But a patient is infinitely more complex than that. So the researchers needed a way to translate a person's complicated medical situation into one of those simple, distinct states that the Markov chain could actually work with. And they did it by creating their own custom scoring system. And this is what's so clever. They found a way to translate a complex human being into a single number. They built a score based on these 6 key factors. And you'll notice it's a mix of things that don't change, like a patient's age, and things that are really dynamic, like complications that might pop up. By weighing all of these, they created one single powerful score to track a patient's overall condition. So using that score, they defined 4 distinct states. First up, state A. This was for low-risk patients, anyone with a score of 25 or less. Next, we have State B, which represented medium-risk patients, with scores running up to 41. Then you have State C for the high-risk group, with scores that could go as high as 57. And finally, State D. This was for patients in grave condition, with a score of 58 or higher. Now, there was also a really important 5th outcome, State E. Think of it as the game-over state, an absorbing state, which just meant the patient had been discharged from the ICU. All right, so we've got the problem, we've got the math, and we've got the patient states. Now for the exciting part, the payoff. Let's see how this all comes together to make some really powerful predictions. The researchers fed their model real-world data. They looked at 64 patient admissions over a 14-month period, and for every single patient, they calculated their severity score, their state, every 2 days. This is how the model learned the real-world probabilities of a patient moving from one state to another. So, what did the model actually predict? The results are pretty fascinating. For a low-risk patient coming in at state A, the model predicted an average stay of exactly 6 days. For a medium-risk state B patient, that predicted stay more than doubled to 12.7 days. That makes sense, right? But here's where it starts to get kind of interesting. For the high-risk state C patients, the predicted stay was actually a little bit shorter, coming in at 12 days. And even more surprising, for patients in the gravest condition, state D, the predicted stay was just 9 days. Now, this probably reflects a very harsh reality of intensive care, where the most critical cases are often resolved much, much more quickly, one way or the other. Okay, so the model generated some very specific, very confident numbers. But here's the billion-dollar question. Were they right? I mean, a prediction is just a guess unless you can prove it actually matches up with reality. So to check their work, they did a classic validation test. They took their 64 patients and just split the data right down the middle. They built the entire model using only the data from the first 32 patients. Then, they used that model to predict what would happen to the other 32 patients and just compared the predictions to what really happened. And the results? They were stunning. I mean, check this out. This chart shows the comparison, what the model predicted versus what actually happened in the real world for that test group. They're nearly identical. This wasn't just some lucky guess. The model was actually forecasting reality with incredible accuracy. You know, a successful test like this isn't just a win for one single research paper. It really points toward a much bigger shift in how we think about managing healthcare and making medical decisions.
And the crucial takeaway is right here, in the study's own words. The difference between what the model predicted and what really happened was not statistically significant. Now, in scientific terms, that's a home run. It means this method works. It provides a real, powerful tool to help tackle an incredibly complex problem.
And all this leaves us with one final, pretty provocative thought. You have to remember, this study came out in 2006. It showed that a pretty simple model could predict something as complex as an ICU stay. So, given the absolute explosion in data and computing power we've had since then, the real question isn't if we can predict these things anymore, it's what are the limits? If a model could do this way back then, what else can they predict now?